Okay, this video is on the metric system, or otherwise known as the International System of Units, or the SI system. So we all know that in the United States of America, we do not use the metric system. We use what is referred to as the English system. So our units are things like the foot and the mile and the cup and the gallon and the inch. And we could go on for a very long time and name units that we use in the United States. But almost everywhere else, all the other countries, or almost all the other countries, use the metric system or the International System of Units, which is abbreviated as the SI system. So who uses it? Almost everyone. And there are actually 3 countries, I believe, the last time I've checked, 3 countries who do not use the metric system. Of course, the United States being the biggest one that everybody knows, who does not use it. And then the other 2 are Liberia and Myanmar, countries that you've probably never heard of. So, if you talk about going to Mexico or Canada or England or Spain or Italy, all of those countries use the metric system, and so they use units that we're not so familiar with. The interesting thing, though, is that the metric system, or the International System of Units, is the language of science. So that's why in your science classes, we always learn the metric system, and we always learn those base units, so that we can speak, per se, in the language that scientists speak, which is the metric system. Now, years and years ago, we used to teach that students had to learn the metric system because the United States was one day going to switch over, which is not true, I don't believe. But now we teach it because it is the language of science. Okay, so who uses it? Almost everyone except for the United States. What's it based on? The cool thing about the metric system is it's based on the number 10. So if you think for a second about our system, and you think about the fact, length is the easiest one to think about that. There are 12 inches in a foot, and there are 3 feet in a yard, and there are 5,280 feet in a mile. Okay, there's no common number there. You can't argue that the English system is based on a certain number. The really cool thing about the metric system is it's all based on factors of 10. So, 1,000th, 100th, 1/10th, 1, 10, 100, 1,000, 1,000,000. It's all based on factors of 10. And so that makes it a little bit easier once you've learned the system to deal with converting between units, which is going to be a topic later in our discussion. Okay, so it's based on the number 10, and it's based on something that we call prefixes. We'll get into those in a little bit, but most of us know a prefix comes before a word. So a prefix would be like re, or un, or those are the 2 that come to mind right off the top of my head. In the metric system, the prefixes are things like kilo, milli, micro, nano, centi, stuff like that you've obviously heard before. And we'll go over that here shortly. Okay, so let's we'll do base units of the metric system. And so we're going to learn 5, I believe. There are actually 7, but 2 of them really don't apply in chemistry, so we only talk about 5 of them. So in the metric system, we have a base unit for length. So, of course, in the English system, we think of length as inches, feet, miles, but that's not metric. So the metric base unit for length is the meter. It gets the abbreviation lowercase m, and the meter is almost the size of our yard. So you might have a yardstick at home, and a meter is almost that same length. So if that puts it in perspective for you. The base unit for mass, or weight, right? Mass and weight are actually different. We'll talk about that. But the base unit for mass is actually the kilogram. So we think about when we mass things or weigh things, we use the pound, right, in America, but that's not the metric unit. So the metric unit is the kilogram, which gets the abbreviation kg. The metric unit for Temperature. Sorry, I lost my train of thought. Most students will say it's Celsius. Celsius is a metric unit for temperature, so I'll go ahead and write that, degrees Celsius. Celsius. But the real metric unit for temperature is the Kelvin, and you may not be familiar with the Kelvin, so we'll talk about it. Kelvin is just capital K, no degree Kelvin, and we will talk about that temperature scale in just a few minutes. The fourth base unit is time. This one seems kind of silly because the time is measured the same way no matter what system you use, and that base unit for time is the second, which gets the abbreviation lowercase s. And then the fifth one is the amount or the quantity of a substance, and that base unit in the metric system is something called the mole. So if you have any, if you're familiar with chemistry at all, you might know that there's something that comes up that's called the mole, and it's not the furry little creature that lives in your backyard under the ground. It's a unit of measure, and it's the way we count things. So a mole's worth of, sulfur atoms, for example, are things that we'll talk about later in this class. Mole can't get the abbreviation M because that's meter, so the abbreviation for mole, as silly as it is MOL, and they just dropped the E, so I don't know, kind of interesting. I want to tell you one pretty cool thing about the mole, so I just ran out of room, but, and we'll get to this much later, but it's an interesting fact. So 1 mole is equal to 6.022 times 10 to the 23rd things. It's not the most perfect science term to use here, but again, remember we're counting. So if you had a mole's worth of, pennies, for example, okay, a mole's worth of pennies, you would have 6.022 times 10 to the 23rd pennies. That's a huge number. Okay, that is the number 6022 with 20 zeros after it. I'm not going to write it because it would take my whole, page here. But that number is huge. It's enormous. And it doesn't make a whole lot of sense for us to talk about a mole's worth of pennies or a mole's worth of marshmallows. But it does make sense for us to talk about a mole's worth of atoms because atoms are so small. So that's why we end up talking about a number that's so big in chemistry, because we talk about things that are so tiny. And like I said, we'll do much more of a discussion with mole when we get to that part of the class. Okay, so let's do some prefixes. Remember, prefixes are what come in front of a word. So when you were, in ninth grade or even in middle school, you may have heard, or your teacher may have taught you the kind of silly phrase to remember some of the metric prefixes, and some students know it and some students don't, but it's something like King Henry died drinking chocolate milk, and it's for kilo, hecto, deca, stuff like that. So I'll go through a couple of the prefixes. I'm just going to do the ones that are most common to us and kind of what they mean in their symbol. So the first one we're going to do is mega, and the prefix mega gets a capital M, and mega is the value. Over here I'll do value. So the value of mega is 1,000,000, or 10 to the 6th power, if you want to think about it in that way. Well, that's a lot, right? It's like, where do you think of mega? Well, you might think of it in like megabyte for a computer. And so mega is big. It's a large quantity of something. Just down from mega is kilo, which gets a lowercase k. And kilo is 1,000. Okay, so kilo means 1,000. So if you have a kilometer or a kilometer, you have 1,000 meters, and that's how this whole idea of prefixes work. Let's see. Then we'll do. We'll go to the smaller ones. We tend to use more prefixes with smaller values. So deci, the symbol for deci is a lowercase d, and deci is a tenth. Okay, a tenth of, so if something is a decimeter in length, it's a tenth of a meter. So there are 10 decimeters in a meter. Following deci is centi. That's probably the one you're familiar with, like centimeters. The abbreviation for centi is lowercase c, and centi is 100th. So if you think about, how many centimeters are in a meter, well, there are 100 of them. And it also makes sense if you think about how many years are in a century. It's that same prefix, centi means 100. And so the centimeter is one that you're probably very, very familiar with. After centi comes milli, gets the abbreviation M, and so you're probably familiar with millimeters. Okay, well, milli is a thousandth. Okay, so we're getting really small. If something's a millimeter, it's very small in length. And there are a couple that we don't often use, but we'll do them just for, actually, I'm just going to do one more, and that's nano. We will use nano in this class at some point, and the abbreviation for nano is lowercase n. And a nanometer is a 1 billionth. So let's see, I think that's 8 zeros and a 1. So there are a billion nanometers in a meter. So a nanometer is very small. Okay, so these are your two larger prefixes that we've discussed today, and then these are your 4 smaller ones. So if we're talking about the meter, right, the meter falls right here. Okay, so then you would have a megameter, a kilometer, the regular meter, the decimeter, the centimeter, the millimeter, and the nanometer. Okay, and that works for anything. It doesn't just have to be meter. It could be the gram, the kilogram, the decigram, the centigram. It just seems that the meter is the one we're more familiar with. Okay, so last thing for this video, I'm just going to talk about the temperature scales. So we don't use Fahrenheit in science class, but that's the temperature scale that we are most familiar with. So, you know that if it's, 42 degrees Fahrenheit outside, you know how to dress. But we're not so familiar with Celsius in the temperature scale that that Celsius is based on, or what value. If you heard it was 18 degrees Celsius outside, do you know, is that hot? Is that cold? We're not so familiar with that one. So let's talk about the Celsius temperature scale. So Celsius, remember, it's degrees Celsius. So I'm going to draw a little, scale kind of thing here. So we'll talk about the freezing point of water and the boiling point of water. So if we're in Celsius, water freezes at 0 degrees Celsius. So I'm going to put 0 degrees Celsius, and then I'm going to put freezing point, okay, of water. And I'm sure you know that water freezes at 32 degrees Fahrenheit. But water boils at 100 degrees Celsius. And in Fahrenheit, that's 212. Some of you might know that. So the difference between the freezing point of water and the boiling point of water is 100 degrees Celsius. Now, the second temperature scale is the Kelvin scale, which is capital K. And Kelvin is a little bit different. So Kelvin, the freezing point of water, is 273 Kelvin. I'm just going to say FP for freezing point. And the boiling point of water is 373. And I'm going to say BP for boiling point. So again, if you notice, the difference in 273 and 373 is 100 degrees. Okay, because of that, there's something interesting about the Celsius and Kelvin scale. And I will get to that in just a second, because before I do that, I want to show you how we convert. So we'll say converting Celsius and Kelvin. So there will be times in chemistry where you have a temperature in Celsius and have to turn it into Kelvin and vice versa. It's very simple to do. You can calculate a Kelvin temperature by taking the Celsius temperature and adding 273. Okay, so for example, if you have a temperature, let's say, of 34 degrees Celsius, and they want to know what it is in Kelvin, to find Kelvin, you take your degrees Celsius temperature, which we said was 34, and you add 273. So, I'll do it longhand here, because I'm not going to use a calculator. And so, that temperature in Kelvin would be equal to 307 Kelvin. Okay, so 307 Kelvin is actually equal to 34 degrees Celsius. So if we wanted to go the other direction, degrees Celsius is equal to Kelvin minus 273. Okay, so these are your two formulas for converting Celsius and Kelvin temperatures back and forth. It's pretty simple. Okay, so then that very last thing I want to mention is the fact that back just a minute ago when we were looking at the difference in the freezing point and the boiling point of water in degrees Celsius, we said it froze at 0 and it boiled at 100. And we said that the difference here, we said that the difference in those two temperatures was exactly 100 degrees. That's what I wanted to do. So it's a 100-degree difference. And we said that water freezes at 273 Kelvin and boils at 373, which again is a difference of 100. Kelvin in this case. So because the temperature scales are spaced out the same way with that difference of 100, there's something really cool about Celsius and Kelvin. And that is that a change in temperature in Celsius is equal to a change in a temperature in Kelvin. Now, didn't need that. Now, if you know the symbol for change, it's a Greek letter and it's a delta, looks like a triangle. So we can also say the change in degrees Celsius is equal to the change in Kelvin. And this is kind of a big deal later on in chemistry. So I'll prove it to you with something very very simple. So let's say let's say you had a glass of water at 67 degrees Celsius and you cooled it down to 20 degrees Celsius. Okay, and we want to know what that change is. Okay, what's the change in those two temperatures? Well, all we'd have to do is subtract them, and we would get it's a difference of 47 degrees Celsius. Okay, now according to this formula right here, it should also be a change of 47 Kelvin, but I will prove it in case you don't believe me. So let's change these two temperatures to Kelvin and then subtract them and see what we get. So to change to Kelvin, remember we add 273. So that would give us, let's see, I'll do it over here, 273 and 67. So this one's 340 Kelvin. And then 20 plus 273, well, that's 293 Kelvin. And if you subtract 340 and 293, you get 47 Kelvin. So what we just proved was this formula, okay, that a change in temperature in Celsius is actually equivalent to a change in Kelvin. Not that 67 degrees Celsius is not 67 Kelvin, but if you lower or raise a temperature by so many Celsius degrees, you also lower or raise the temperature by that many Kelvin. And so that's an interesting thing about those two temperature scales.